An empirical formula is a formula that has been reduced, so it shows the smallest whole number ratio. And we can find the empirical formula for an unknown substance by taking the amount of each element in the formula, finding the moles of each element, dividing it by the smallest number of moles, and then getting the subscript. So we're using moles to find the ratio between the elements involved. Because we know that percentages always add up to 100, if we assume 100 grams of a substance, then these percentages just change to grams. And we can take 32.38 grams of sodium and convert it into moles. So you put grams of sodium on the bottom, mole of sodium on the top. One always goes with mole. Grams is the molar mass, which for sodium is 23. Do the same thing for the sulfur. 22.65 grams of sulfur. Grams of sulfur on the bottom, mole of sulfur on the top, 1 mole. Molar mass of sulfur is 32.1. And then again the same thing with the oxygen. 16 is the molar mass of oxygen for every 1 mole. Then we're going to divide by the smallest. So sulfur is the one that has the smallest number of moles. So we're going to divide all 3 of them by that value. And again, what we're doing is we're trying to find the ratio between our elements. So that would give us 1 sulfur, 2 sodiums, and 4 oxygens. So then we're going to write our formula. We're going to take these values as the subscripts. So we'd have Na2S1O4. To name this, there's 3 capital letters, so it has to contain a polyatomic. Because the first one is a metal, it's not an acid, so we're just going to name it sodium, and then the polyatomic sulfate. Here we have a sample that is 10.15 grams, and it's known to contain phosphorus and oxygen. And then it tells us the amount of phosphorus. It doesn't tell us the amount of oxygen. So if 10.15 grams is for phosphorus and oxygen, and we subtract the mass of the phosphorus, then what we're left with is the mass of the oxygen. So we have 5.717 grams of oxygen. Now I can take my grams and convert them for moles for both the phosphorus and the oxygen. So grams of phosphorus on the bottom, mole of phosphorus on the top. 1 goes with mole. The molar mass of phosphorus is 31.0. Molar mass of oxygen is 16 for every 1 mole of oxygen. And then we divide by the smallest. And that would give us 1 phosphorus. And when we divide the oxygen, we actually end up with 2.5 498 or 2.5 oxygen. The 0.5 is something that you have to watch out for. You can't have half of an atom. So instead, you're going to multiply both of these by 2. So really we have 2 phosphoruses and 5 oxygen. So when we write our formula, it's P2O5. So watch out for the 0.5 when you divide by the smallest. Now to name this, I have 2 capital letters, so it's binary. Both of them are nonmetals, so it's a binary covalent molecule, so I use my prefixes. Diphosphorus pentoxide. A molecular formula is a multiple of the empirical formula. In other words, it's not reduced. So, looking at these formulas, we can label empirical or molecular without doing any math whatsoever. If you're given a formula, you don't need to do math. So, C2H6, if we look at the subscripts, that would be a molecular formula. If we reduce that, divide them both by 2, we get CH3 as the empirical. Here we have a 1 and a 2. That's already been reduced, so that is the empirical. Here I have a 2 and a 4, so that is a molecular because we can reduce it, and it would reduce to NO2. Now you could divide by any value. It doesn't have to be a 2. The example 1 and 3 just happen to be reduced by 2, but you could be reduced by any value. If we want to solve for this mathematically, it does get a little bit more complicated. However, the first steps are the same as finding the empirical. So we have to change the percents to grams and then convert them to moles. The molar mass of hydrogen is 1. Oops. So then we're going to divide by the smallest. And it's actually a 1-to-1 ratio. So the empirical formula is CH. I want to find the molecular formula. Well, the molecular formula is a multiple. To find the molecular formula, you take the molecular molar mass and you divide it by the empirical molar mass. That will give you your multiple that you multiply the subscripts by. Now, something to keep in mind, the molecular molar mass is always given to you in the problem. The empirical molar mass you calculate based on the empirical formula. So if we look at the problem, it tells us that the molar mass of naphthene is 128 grams per mole. If we look at the empirical formula, we have 1 carbon and 1 hydrogen. So the molar mass of the empirical would be 12 plus 1, and we would get 13. So the empirical molar mass is 13 grams per mole. And we get a multiple of 10. So that means I'm going to multiply my subscripts by 10. So C10, H10 would be my molecular. Tetrafluoroethylene has carbon and fluorine in it. So the first thing we want to do is find the empirical. Change those percents to grams. Take our grams and change it into moles. Fluorine has a molar mass of 19 for every 1 mole. Then you divide by the smallest. And then you can write the formula. So this is my empirical formula. To find the molecular formula, you take the molar mass that they give you in the problem, 100. You divide it by the empirical formula's molar mass that you have to calculate. So carbon has a molar mass of 12, plus we have 2 fluorines, so 2 times 19. And we get 50 as our empirical molar mass. So we'll say 100 divided by 50, and that gives us a multiple of 2. So then we multiply the subscripts by 2. C2F4 would be the molecular formula. The table shows data from an experiment to determine the formulas of the hydrated barium chloride. Determine the formula for the hydrate and its name. So what we're doing here is we're solving for the X value. We have the mass of the empty crucible and the mass of the hydrate plus the crucible. So how would we find the initial mass of the hydrate? Well, all we have to do is subtract 31.35 minus 21.30. That tells us that the mass of the hydrate is 10.05. After we heat it, the mass of the hydrate is now after we heat it for 5 minutes, we have a mass of 29.87. But what that is the anhydrous, or the compound without water, and the crucible. So if we take our mass of the crucible, or take the mass of the anhydrous and the crucible, subtract out the mass of just the crucible, then we know that the mass of the anhydrous is 8.57 grams. So we have the mass of the hydrate and we have the mass of the anhydrous. So how much water do we have present? Well, if you take the mass of the compound with water and you subtract the mass without water, we would know that the water was 1.48 grams. So now it's an empirical formula problem. We're going to take the mass of our water and convert it to moles. Molar mass of water is 18. And then take the mass of our compound without water, which was 8.57 grams. Now the compound without water would be barium chloride. So 1 mole of barium chloride, we'll need to find the molar mass. So barium has a mass of 137.3, plus we have 2 chlorine, so 2 times 35.5, and it has a molar mass of 208.3. And we get 0.0411 moles. And then you divide by the smallest. Okay, so that tells us we have 1 barium chloride and 2 water. So if we come back up here, that means X is 2. So the formula is BaCl2 dot 2H2O. So how would you name it? Well, we already know that BaCl is barium chloride. The prefix for 2 is di, and because its water's attached, it's a dihydrate. There's 2 waters attached. So the name would be barium chloride dihydrate.